right, we want to explain the meaning of each of the terms in the equation delta E equals Q plus W. Well, the delta E represents the change of energy of a system, so the E is energy. And we are looking at the change of it because that's actually easier to measure than it is to measure the energy of a stationary phase. And when that change occurs, the energy is released or measurable in the terms of Q and W, where Q is the heat and W is work. All right, question 2. If Q for a process is a negative number, then the system is doing what with its energy? Well, it's not gaining it, it's actually losing it, meaning that negative value. And that is a situation where technically it gives off heat. It would be a situation where the container or the reaction would feel like it's producing heat or getting hot. All right, number 3, couple different ways to do this. Using our formulas, we could see that Q, the energy that's given off, is related to the specific heat of the substance, be water in this case, times the mass of the water, times the change in temperature. Now, on this particular one, I could just plug in some numbers. 654 would go in for our Q, and specific heat of water is 4.184 joules per gram degrees Celsius. Mass is 5.51 grams. And we would then be able to calculate how much the temperature goes up. All right, now, once we have that number, we just redo this calculation. Because it says we want to warm the water by the same amount, so the delta T would be whatever we solve this one for. We'd solve for our Q. It's 55. All right, but nice thing about math and the trends, if we look at it, since the 4.184 and the delta T are kind of constants between these two, we're kind of looking at the ratio between our Q and the mass. And if you notice that the mass just goes up by an order of 10, the temperature would have to go up by an order of 10 as well. So whether you solve for the temperature and then plug it in here and solve this equation, or if you look at the logic here going off, you'll find that the Q is 6,540 joules. All right, number 4, it is just some conversion factors. I'm going to forget the little the equal sign, and we're just going to put in our conversion factors. Now, I don't really have anything from kilocalories directly to joules, but I do have calories to joules. So we will start by turning our kilocalories into calories. And then for every calorie, there is 4.184 joules. Therefore, 75.2 times 1 divided by 1. How about times, there should be 1,000 there. I'll fix that here in just a second. Times 1,000, and then times 4.184. And we get that this is, 316,000. I need to come back over here, and because that's 1 kilocalorie is 1,000 calories. All right, next one's a little bit easier because since it's already in calories, we just need to do the 4.184 joules into calories. And since it's the same value, that's just going to move our decimal, 316 joules. All right, the next one wants to go from joules to kilocalories. That's kind of undoing what we did up at the top. So we would start by dividing by the 4.184, and then we need to turn our calories into kilocalories. And 75.2 divided by 4.184, and then divided by 1,000. It's going to be a small number. 0.0180. Very similar, but we have the kcals in front. So we will convert kcal or kilojoules into just joules. And then we're doing a repeat of the calculation above. Calculator wise, I wouldn't even bother with the 1000s. I actually could just take the 75.2 and divide it by 4.184. And we get the exact same number as before, but the decimal's over 3 places. So 18.0 kcals. Or calories, sorry. Oh, wait. Kilojoules. I went to kilocalories. Back up. Forget that conversion factor. Forget that. So I need to multiply this by 1,000. So this, I've lost my pen, is 180,000. Because we would, no, it's just 18,000. So we just multiply this by the 1,000. So I got one too many zeros. 18,000 calories. Sorry about that. Russian, messing up. All right, number 5 is going to use the exact same equation we used for number 3, which is the Q times specific heat times the mass times the delta T. And I've given you everything except for the specific heat. So we have 69.5 kilojoules. The C is an unknown, and we have 1,012 grams. And we see that the temperature increased by 11.4 degrees Celsius. And since it says an increase, that is your delta T. So not giving you 2 temperatures, we just told you how much it increased by. All right, now technically we're solving for C, but if you notice it wants our specific heat in terms of joules per gram degrees Celsius. So when I actually put this in the calculator, I'm going to take that 69.5 and immediately convert that to joules by multiplying it by 1,000. And then I'll divide by the grams. And then I'll also divide by the temperature change. And we get that this specific heat is 6.02. And yeah, I just have 3 significant figures, so 6.02 joules per gram degrees Celsius. All right, another one of these to apply this, I am going to use the exact same equation. This time, giving you the joules, or the Q, also giving you specific heat, and the mass. Now it wants to know how many degrees the temperature increase would be. We're going to solve for the delta T. So 125 divided by 0.24, and also divided by 29.3, and we get the change of temperature about 17.8 degrees. All right, what is next? Next one's applying or getting our heat from a delta H or an enthalpy. Now, this can be a little bit easier or harder based on how we're doing it, but I'm going to help you see the confusion we can put in there. All right, so I give you the balanced equation, and it is balanced, and I give you the delta H for it, and I want to know the quantity of heat released when 1 gram of sulfur is burned. And it does specify the excess oxygen. In theory, this could be a limiting reactant type thing. I could give you a gram of each and then ask you how much heat's being produced, and you basically have to figure out which is going to be limiting between the two reagents before you figure out which one produces the heat. But we're not doing that. This game, I'm telling you there's sulfur, and we're assuming there's plenty of oxygen, excess oxygen. So I'm going to start by converting this into moles, which would be 32.06 grams. All right, once it's in moles, now we actually can relate this to our delta H, because this is something neat. The delta H can be turned into a conversion factor. Now, this one specifically says moles of SO2, but it's kind of actually just moles of whatever's in the equation, assuming it's balanced and all that. But this is balanced with a bunch of ones, so this is saying there's 296 kilojoules per 1 mole of sulfur burn up, or 1 mole of oxygen burned up, or 1 mole of SO2 being produced. So since I care about the sulfur, that's what I'm going to put into the equation. So I just take 1 divided by 32.06 and then times 296, and I will flip the sign when I print it out. There should be a negative there, obviously. And this is a mere 9.23 kilojoules. Negative. All right, next one's a little bit easier because I'm just giving you moles, so I don't need to convert them to moles first. And it does say moles of sulfur, so we're going to do the same type of thing. The balanced equation said that that's the energy per 1 mole of sulfur, 1 mole of oxygen, or 1 mole of SO2. So we just do the 1. And 0.501, I got to fix that, times 296, we would see that that's a mere 148 negative. So 0 and 1. And finally, 1 mole of SO2. So 1 mole of SO2, we'd still have that same value up top, 296 kilojoules, but you'll want to look at your equation. The moles we can put in there, but we have to have the coefficient there. So this is still just 1, but now we can say it's in terms of SO2. Now, something weird, as this reaction goes forward, the system or the reaction does require that heat. But if it wants to know what quantity is reduced to break it or required to break it up, this is really what's going to be coming out, because it is an exothermic reaction, is a negative reaction. So it is still negative. All right, number 8 is a challenging problem because I gave you the 3 reactants. Early on in our chemistry career, we normally do this type of reaction with just 3 equations, but this adds a little bit of a challenge onto it, makes it a little bit harder to do. But the process is the same in every single time that we do these. So what we're going to do is rebuild our overall equation using these 3 equations. And we're going to do them at component at a time. So what I mean by component at a time, you notice that first reagent is NO as a gas, and we have it right there in equation 3. Now, what we're going to do is just rewrite equation 3 then down here. And just like it is. All right, now we're going to do that with other components. Now we got to be careful on this. I'm going to actually highlight this in blue, but this O2 is actually found in more than one equation. So since it's in all of our equations, I'm not going to do anything with the O2 yet. And I also am not going to do anything with the NO2 yet either, because that's our next reagent. And that's mainly because it's only found in that third equation. And we've already taken care of the third equation. All right, so the next component I'm going to have us give us anything beneficial is the actual O by itself, atomic oxygen, because that's only found in equation 2. So I'm going to rewrite equation 2, and I want to change the coefficient so it's only 1 O2. So I'm going to actually multiply all the coefficients by 1/2. All right, now, since the O2 was found in all of our equations, we're not going to be able to do anything with it yet, but we do know that we're going to do something with equation 1 to fix all this, because that's where the O2 gets balanced out. All right, to figure out what we need to do, what we're going to do at this point, and this is not going to give us the overall equation we want, we're going to combine our reagents from equation 3 and 2. All right, and that one, once we've done this, now we're going to look at them and see what do we need to get rid of, or what is wrong comparing this to our original equation. And right off the bat, I see on my reactant side, I have these ozones, O3s, and they're not found in the overall process at all. So I'm going to build my new equation 1 off just that factor. I want O3 gone. So when I rewrite my third equation, or my equation 1, I want O3 as a product instead of a reactant. So I am going to reverse it. But I want one O3 because I want it gone. So I'm going to multiply all my coefficients by 1/2. Now, if I do that, that would give me 3/2 of an O2, 3 times 1/2, and then that O3. That 3 looks terrible. All right, but that gives me something kind of neat now. So when we combine our equations now, we're going to be basically adding let's add the red and the green that I just did, because we can do something kind of cool. You notice how this O3 is the only product on that new equation? Well, it counterbalances that one. That side and these two, they cancel each other out. And 3/2 O2 would add together with that 1/2 O2, giving us 2 O2s. I can write that right here. So that would be 2 O2s. But those 2 O2s would cancel out one of these. So one of those would bring that down to 1. All right, when we total up all the things we've removed, and let me go back to the green. We have the NO gas that we didn't do anything with. The O3 went away. That half of an O2 and this 3/2 an O2 combined to make 2 O2s, and then we removed one of them, so there's just a single O2. And on the product side, there's an NO2 and just an O. But by combining these 3 equations in this way, we created this overall process, which means we can add these up. Now, not like they are. Equation 3 was fine, but equation 2, we had to actually multiply all the coefficients by 1/2. So we're going to divide that by 1/2. And equation 1, we did the same thing, but we also reversed it, which would mean we would reverse the sign. Now, my calculator's in the way for this one. So we have proper answer here is 427 divided by 2 plus 495 divided by 2 minus 199. And if we did all that right, if I did the math right, this new delta H is, 262 kilojoules. Make sure I agree with that. Reversed it. Yeah, I like that one.